All right, welcome back. Today we're going to be looking at a concept known as polarization, and this is coinciding with Module 7, Inquiry Question 2, the wave model of light. So just have a look here. We are trying to conduct investigations to quantitatively use the relationship of Malus Law. So we'll briefly mention that today. For the plane polarization of light to evaluate the significance of polarization in the development model of light. So how does polarization prove the wave model of the light? That's what we're looking at. In previous discussions, we've talked about what was first initially said about light waves. So Christian Huygens believed that light behaved like a wave, not a particle. He did have some errors in his predictions. He thought that light would act like a longitudinal waves, like sound. Here's an example of what polarization looks like. You can see on the right-hand side here, the light here is really bright, and it's really hard to see the boundaries of this hilltop mountain. While as you see here for polarization, what's actually happening here, the image appears to be darker. So what we could say as a good starting point is if light is polarized, it's the same thing as saying we're filtered out the intensity of light. So that's what we're looking at here. That's what polarization does. It filters out the intensity. How does it do that? Well, imagine this. Imagine we have a Polaroid or polarizer, and it kind of has these little slits in between that mitigate certain vibration. You can see here we have unpolarized light. Now, what could that be? That could be something like light from the sun. When light from the sun comes out, it has electromagnetic radiation vibrating in every single direction you can think of. So that's what we're seeing here with unpolarized light. When we have a polarizer, this one is a vertical filter. What that actually means is it only allows light that's vibrating vertically up and down to pass through this polarizer. We call this a linear polarizer because we're only blocking, or we're only allowing one orientation to come through. So that's what we see here. You can see that no matter how they're vibrating, any wave that's not vibrating vertically is blocked out. And so that's why we see a decrease in the light's intensity. So if we want to try and explain this, you can only really explain this as transverse waves. Longitudinal waves, if you could imagine, wouldn't be blocked out, basically speaking, because longitudinal waves is going backwards and forwards, so I would still keep going backwards and forwards through our picket fence analogy. So, defining polarization. Polarization is defined as the blocking of transverse waves on a single plane. What I mean by a plane, vertical, horizontal, something like that. Light is a transverse wave because it oscillates perpendicular to its direction of movement. If we have a transverse wave that's oscillating horizontally, it cannot pass through a vertical slit. So we have an example here. This one's vertical. It's passing through a horizontal slit. The only orientation it has is to go up and down vertically. So it cannot pass through the horizontal slit of the polarizer. And like I said, this demonstrates that light behaves like a transverse wave because transverse waves has an orientation of vertical, horizontal, at different angles. If you were to do that for longitudinal waves, as you can see in this diagram here, the wave will just be compressed backwards and forwards, but there is no orientation that's being blocked from going through. So you can lower the intensity of light using a Polaroid, but you can't lower the intensity of sound using the same technology. Okay, So that shows that electromagnetic waves are transverse. We've talked about this before, and it makes sense because the way that electromagnetic waves are produced, as stated by James Maxwell, is that you have a propagating electric field first. So you have a changing electric field. That changing electric field, as we know, will also induce a changing magnetic field. Now, if they're both changing, you essentially keep producing, they keep propagating, they keep inducing each other. And so that's how electromagnetic radiation works. It's just magnetic fields and electric fields inducing each other, making it move along. You can see polarization as well in the surface of water. Now, perhaps you might wonder, why does water polarize light? Well, water is made out of a molecule called H2O. When it's in a solution, it breaks down into hydrogen ions and hydroxide ions. They're going to be moving backwards and forwards. Okay, they're going to be moving in a particular orientation in the water. So when light comes through, they also act like a little filter to block off the light coming through as well. So, that kind of explains why it's a bit darker in water than it is outside, besides the fact that obviously intensity is also affected by distance. Okay, when it comes to the naming system, this is what we have here. We have unpolarized light. As you can see, this diagram here kind of represents that light is vibrating in every single direction you can imagine. When it comes through the vertical polarizer, the very first polarizing filter you have is what we call the polarizer. So that's our filter number 1. Okay. When it comes through, the wave that we produce is known as the vertically polarized light because it's gone through a vertical filter. If we go through filter number 2, so a second filter, or polarizer number 2, we call that an analyzer or analyzer 1. Okay, so that's what we have. If you were to have a third polarizer, we call that analyzer number 2. Now what we can see here is if the first polarizer and the second polarizer are 90 degrees to each other, so they're perpendicular to each other, the intensity of the light is 0. So you have two Polaroids. If they are perpendicular to each other, that is 0. Same idea, if you have a Polaroid filter, the very first one will halve the initial intensity. So the maximum possible intensity we have here, that is halved when light goes through one Polaroid. Okay, so unpolarized light is passed through a filter in that particular orientation. The wave of that same orientation will be the only one that passes through. We call that plane polarization. And light vibrates only in a single plane. That's what we have polarized light. So let's try and show this as an example. Here we have unpolarized light because it's vibrating in all directions. Here we have a vertical polarizer or vertical polarizing filter, however you want to call it. And here we have polarized light in the vertical orientation. So it's a vertical polarized light. So that's kind of how you can actually control the intensity of light by using these things called Polaroids. Right, what are they made of? They're made of microscopic heteropentite crystals and also polyvinyl alcoholic plastics with some iodine in it. You can make many things using Polaroids. You can use any old glasses and some sticky tape. You can also do the exact same effect. You can also do the same idea with polarization in real life. So there's that. All right, the next thing we can show is actual simulation of how polarization works. All right, so this is what we have here. Okay, we have polarization of light. Let's have a look. So we're running it through. You can see that the light is traveling through here. Okay, and only the vertical component is allowed through. If I rotate the second polarizer 90 degrees, we've basically prevented the vertical vibrating light from coming through. And therefore, we have a completely polarized light at intensity of 0. Let's say if we do it at an angle, let's say 45 degrees here. Okay, so 45 degrees between the first and second. Let's make the third one 90 degrees. So the third and the fourth, or the third and the first one, sorry, they are perpendicular to each other. But as you can see, the first one, between the first one and the third one, there's still light going through the third one here. Okay, the reason being is obviously light has a component, has a horizontal and perpendicular component. This is still allowing some of that parallel component to come through, and so there we have that. So that's why it's still vibrating through here. As you can see, if we then put a filter that is perpendicular to our third one here, again, 90 degrees perpendicular to each other, no light goes through. So who kind of exemplified or demonstrated that this is what we see right now? Let's have a look. Okay, so just to start off with, the intensity of light passing through the first filter will give you an intensity of half the original. Okay, so this is the original light source. That's the intensity. If we pass the first filter, we will have half of that intensity there. In your datasheet, you will also be given a replacement called Imax. Means exactly the same thing, the original intensity we're talking about here. So that's what we're looking at. If we're measuring intensity of light, it's measured in a unit called candela, which also is CD. Sometimes they will also use lux. So that's also another unit that can be used to represent intensity of light. So, like we said, if the angle between the polarizer and the analyzer are parallel to each other, then you have maximum intensity. So from the first filter here to this one here, assuming the angle theta is 0, then whatever this was, let's say this was half of the original here, this would also be half of the original if theta between the two filters is 0. If theta is at right angles, then the perpendicular component blocks out all the light, and then you have an intensity of 0. So theta between the first polarizer and the first analyzer is 0, or whatever combination you have, 90, sorry. So perpendicular to each other. Then the overall intensity of light would be 0. This is governed by a concept called Malus Law. So the idea is the analyzer, or the light transmitted by the analyzer, is directly proportional to the square of the cosine of the angle between the transmission or axes, the analyzer and the polarizer. So this is the general formula we can see. There's a general proportionality between the intensity that's coming out of your analyzer or polar analyzer and cos squared theta. Okay. If there was more than one analyzer, obviously you could see that there are successive calculations we can do. this is the formula for Malus's law. So that's just to say that the intensity that you're measuring, so the light intensity, or the one that's polarized, is equal to the original source. So that could mean two things. That could mean you have a light bulb and it creates unpolarized light, goes through filter 1. That could be I0. If you're looking at exclusively perhaps after it goes through 2 filters, so this one here and then this one here, I would be the one you measure here, and the intensity of light that's coming through the first filter would be I max there. Again, it's measured in CD, candela, and this is known as Malus's law. So if I was to graph out the intensity of light, because it's cos theta, it will look like this at 90, at 0 degrees, at 180. That's the intensity of light that I should be seeing there, like a cosine function. Okay, let's have a quick look at some questions. So we have unpolarized light going through a polarizer with intensity IO. What will the intensity of the energy or the polarized light be expressed as a percentage? So if IO is the original, we said if it passed through one polarizer, IA will be half the intensity of IO. Okay, so if we compare that as a ratio, IA is 50%, or IO is, or IA will be 50% of IO. Now, say in the next one, we are trying to find the polarized light. So we have a second analyzer. So we have one here, we have two here, okay? And say this analyzer, instead of being 90 degrees, it's 60 degrees to this one here. What would the percentage be then? Well, we then need to work out the original intensity again. The original intensity we got was the 50% cos squared theta. Okay, so the maximum percentage we have is 0.5 cos square 60 degrees. Okay, or you can do cos 60 squared, works either way. You'll find that the overall intensity drops down to 0.125 candela. And so the percentage compared to the very first original, so the unpolarized light, Imax, it is 12%, 12.5% of Imax. And that's what IB would be. Okay. Let's have a look at the next set of questions. So we have emerging light then falls upon a second analyzer, an axis of 30 degrees to the first analyzer, 90 degrees to the polarizer. So we tried to picture this out. We have our first polarizer goes through here. We have our second analyzer here, and we have a third. So the third one is 90 degrees to the first one. So this can be horizontal, this can be vertical. But it is 30 degrees to the first analyzer. So we could imagine this to here is 30 degrees, which means this to here is about 60 degrees. Okay. So using the value we had before, which was 0.125, what is the new intensity of light coming here at IC? Substitute it in. The original was 0.125 cos squared 30. And then we get 0.09375. So we have about 9.375% of the original intensity of light coming through in the third polarizer or the second analyzer there. If we then remove the first analyzer, so we get rid of this, what is the intensity of light? Well, at that point in time, the first and our new second are perpendicular to each other, so 90 degrees to each other. So intensity of light would be 0. Okay, so how does this kind of explain the whole concept of the wave model? Well, you couldn't really explain this with the wave particle or the wave, sorry, I'll say that again. You can't explain that with the particle model of light, simply because if it's light particles, the concept of the picket fence, similar to longitudinal waves, wouldn't stack up because the particles can just go straight through these gaps and you'll get imprints of light, kind of like little straight barriers type stuff. The fact that you can only witness this concept of polarization is due to the fact that light is behaving like a wave in this circumstance. If the two Polaroid filters are orientated perpendicular to each other, all the light is blocked out. Okay, if light did behave like a particle in this context, the particle should still be able to go through these gaps and you should still be able to see light. But that's not the case. All right, next question we have. We have 3 polarizers and we are trying to calculate the intensity of light transmitted between each of them. So we're going to call the first analyzer I1 and the intensity of analyzer 2 will be called I2. Simply put, cos theta for the first one, we already know that the intensity of light is halved as it goes through the first one, so it's 0.5 the intensity. The analyzer is 30 degrees to the original polarizer, so cos squared 30, we get a value of 0.375 CD. Do the exact same thing. We know that the second analyzer is 60 degrees to this, which means it's 30 degrees to our other analyzer. And so we get that value there, about 0.281 CD. The final one we have, a little bit more different. We've done many that have related to finding the intensity. This time we're going to try and find the angle between the two Polaroid filters. Okay, so we know that the intensity of light is 1/8 of the maximum. 1/8 of the maximum. We want to find the angle. So let's substitute that in, shall we? We're going to say that I is equal to 1/8 of I max. And we're going to substitute that into the equation here. That's what we get at the bottom here. As you can see, Imax and Imax would be the same thing, so they cancel each other out. And we get the following here. Cos squared theta equals to 1/8. Now, this can simply be read as cos theta squared. Okay, so if I want to get rid of the square, I square root both sides. If I square root both sides, I get cos theta 1 over, or square root of 1/8. If I then want to move cos over that, I get the inverse, or if I want to get theta, I will get the inverse cos over 1/8 squared, or rooted. And that gives me an angle of 69.3. Remember in your calculators to do this in degrees, not in radians. That will give you a different type of answer. So there's that. That's how you actually look into Malus's law. That's how it's applied. What we're going to look at again in another video is just, the application of Malus's law, actually doing an experimental calculation on it. So we'll see when we have time for that. Just a little summary of what we talked about here. So just remember, Malus's law is about polarization. Polarization being changing the intensity of light by using different filters. And the reason why polarization really pictures or really supports the concept of the wave model of light is you can't see this phenomena in particles, right? So you can't block particles if there is a gap going through. If you have a fence and you're throwing a rock into the fence, if it goes through the gap, the rock will go through. That's not the case with light. Light will be blocked from vibrating, and hence it doesn't go through. Okay, so this is the topic on Module 7, Inquiry Question 2, about polarization of light. If you want to see the links to other Inquiry 2 questions, that will be in the link in the screen here. And if you want to watch something else, another kick off there. Anyhow, that's all there is to it. Nothing else.